tells us that if you take a massive object and compress it to a very high dense uh, configuration, then it collapses to a singular point where the density becomes infinite, the curvature of the space-time geometry becomes infinite, and it is shrouded by a fictitious spherical surface called the event horizon. And what's an event horizon? General relativity tells us that if there is an event which takes place beneath the event horizon, we can never see it. The outside, if there is an event which of course we will see, but it will take a long time to reach us, but nothing from inside the event horizon can ever escape. So in classical general theory of relativity, a black hole will only swallow matter once the matter enters the event horizon. Then that's it. The matter just goes and hits the singularity and nothing can escape. And therefore, the black hole will just appear black. And the hole comes because the point singularity is like a hole. The matter just goes inside the hole forever and we don't see it. So next slide, please. So the only way to observationally look for black hole is there are many binary systems like two neutron stars coalescing or a black hole and another star rotating around it. Then gas from the other normal star, as it comes and falls into the black hole, it forms an accretion disk. And this accretion disk, because different regions move with different velocity, so therefore elements, they rub against each other and the accretion disk becomes very hot and starts emitting X-rays when the accretion disk attains a temperature greater than 10 million degrees Kelvin. Then such a accretion disk is a copious source of X-rays. So X-ray sources are likely to house a central black hole. This is so far as classical black hole is concerned. Stephen Hawking for the first time showed that if you take quantum mechanics into account, then quantum mechanics predicts that a black hole also radiates by means of quantum tunneling. Unfortunately, the temperature of a black hole is inversely proportional to the mass of the black hole. For example, if you take sun and compress it to a radius below 3 kilometers, then the sun will of course become a black hole, but its Hawking temperature will only be 10 to the minus 7 degree Kelvin. It will be too cold to detect Hawking radiation from it. Let's go back. So what I want to summarize the essence of general relativity is by analogy. Remember, this is just analogy. The real understanding comes only when one goes with the mathematics of tensor calculus. But pictorially, what one can think of is, supposing the space-time is a two-dimensional rubber sheet, then what Einstein tells us is that if you have a massive object, its energy and momentum, if you put such an object, it will sink in and it will distort the geometry of this two-dimensional rubber sheet. And more the mass is, more the object will sink and cause a greater distortion in the surface geometry of the two-dimensional rubber sheet. And in this two-dimensional rubber sheet, after all, everything would move in the shortest possible direction, but what is the shortest possible distance depends upon the geometry itself. So that is what general theory relativity tells us, that gravitation is nothing but the manifestation of space-time geometry. The most important prediction of general relativity is the fact that if you have matter distributed in an uniform and isotropic manner, then general relativity predicts that the geometry of such a configuration of uniform matter is that either it tells that the system expands or it contracts. Einstein could have predicted from general theory of relativity the fact that galaxies are distributed in uniform and isotropic fashion, he could have predicted that according to his general relativity, the geometry of such a universe must be an expanding geometry. So he could have in fact predicted about the Big Bang universe. It was Hubble who, through his astronomical telescope, deduced that the geometry is expanding and led to the idea of Big Bang universe. You have to go forward to many slides ahead. So, general relativity predicts that if galaxies, matter, everything is uniformly distributed, then either the system will collapse or expand. It depends upon the initial condition. It so happens the initial condition was that was an expanding universe. So from astronomical observations, we know that the universe is indeed expanding. In other words, take the analogy of a raisin plum cake. Then if the raisins and the plums, they denote the galaxies, and the substratum of the cake is like the space-time, then what we have from general relativity is that the space-time geometry is expanding so that the distance between any two galaxies is increasing. And this is what we observe from astronomical telescopes. In other words, general relativity in essence predicts that there is a Big Bang, in the sense that in the past, when the universe was created, it was extremely dense, and as the time went on, the universe expands, and expansion obviously means cooling down. So initially the universe was very hot, but today, here we are today, because of this hot ball of gas expanded to such a large extent, it has cooled, and the relic temperature is about 2.7 degree Kelvin, and which has been observed. So isn't it a strange result that Einstein's general relativity in a way predicts the Big Bang origin of the universe? What could be more successful than such a theory of geometrification